All right, so we talked about there we go, dipole. And being able to draw Lewis dot structures is going to really help you out. So if you're struggling with Lewis dot structures, that's something that I would encourage you to give yourself a little bit of practice on, okay? I think most of y'all know how to do Lewis dot structures because people who struggle with that generally don't get in here. But work on that. Make sure you can do that. Make sure you can translate the electrons that are on the periodic table to the structures and how they would join together. Because that's going to help you see about things like whether or not things have a dipole. And remember, that simply, is it polar or not? And so you can ask those two questions, right? After you draw your Lewis dot structure on the central atom, we're going to say, are there any lone pairs? And is anybody different? And if the answer to either of those is yes, then you've got a polar molecule. And if you have a polar molecule, that means you have a dipole. Because in order to be polar, one's got to be slightly positive and the other's got to be slightly negative. Once you have a dipole, you can then have your dipole-dipole interactions and your intermolecular forces and those kind of things. Do be sure collisions is posted, so make sure you work your collisions. Right now, I think phase changes is coming up due. Okay, so knock through that. That's pretty straightforward, so you should be able to handle that.
I thought on the Canvas calendar it says it was due Monday.
Yeah, it was due Monday, yeah. What? The 11th. So get that done, please. I haven't opened them to grade, so I'm not going to count late points if you can get it done today. Then do a screenshot or shoot.
I think it was 11 or 14.
Yeah, so just shoot me a screenshot of it. I've done that in the past where you kind of make a video of how to solve it. Yeah. That's another good reason to do this work early on so that you can get help before it's due. Yeah.
On the textbook guide, I can't find the 8.5 figure, so I just left it.
Did you get the one that says version 10? That's
on the online one and on.
Yeah, so in the module, there's a one that's version 10. I can show you that, yeah.
So also on the reading guide, there's this small, very small section about polymers. Are we going to talk about those?
So I want you to read that. That's 22.5.
I couldn't find it on the online book. I had no idea what 22.5 was referring to.
So it should be in your, it's 22. This is the online book, so it's the same.
Chapter 22, section 5.
Yeah, chapter 22, section 5.
I just Googled it. Okay, yeah, that makes sense.
Yeah, no, it's right here, and it should be in your. It's right here.
All right.
Okay, so it should be the same. And this is the same as the online book.
I was also looking for table 8.5, but I have the actual hardcover book. And
Yeah.
I couldn't find it.
So table 8.5.
I think it's 8.6 actually. I just skipped it.
Yeah, I was 6.
Will this reading guide be it?
Yep. Yeah, it's right here. That's on page 323. Page 323 is table 8.5 and 8.6. I have started that because those reading guides are written on version 8, and so there are occasionally differences. But yeah, it's way far away from table 8.4. It's like much later. Because figures are numbered separately from how tables are numbered. Okay, so it's page 323 in the 10th edition, which should also correspond to the online. So yeah, and they're asking you comments about that's the bond length and bond strength stuff. So kind of thoughts about that. Yeah, I did actually check that one. I've missed them in the past. So when you come across that, feel free to email me or shoot me a remind. Hey, where's this table from the reading guide? Sometimes they've moved it slightly from version 8, again where the reading guides were written from, to version 9 and then 10. So yeah, if you come across that, just shoot me an email or a remind and let me know what you're missing, what you're looking for. All right, quiz time. Y'all ready? You can handle that. Which of the following is the most polar without being considered ionic? You can look at a periodic table if you want to. I don't think you really need to, because you know which one's ionic. Do you? Okay. Remember, this is chemistry. You should definitely have your periodic table out in front of you so you can. Remember, I want you to go ahead and make a commitment. Write one of these little baby letters down, A, B, C, D, or E, or F. Yeah. We got something written down. Cool. So let's look at A. First of all, is this going to be a polar covalent, or ionic, or nonpolar? All right, so I'm going to say this is PC. This bond is going to be ionic, so that can't be right. This bond is going to be polar covalent. This is going to be nonpolar covalent, right? Definitely nonpolar. Because it's oxygen, so they're equal to each other, right? So the electronegativity difference between a diatomic is going to be 0. If you remember our little list, right, we had a 0 to 0.3, we're going to call nonpolar, and then 0.3 to 1.7 is polar covalent, and then when you get above 1.7, it's ionic. Okay? All right, what about this one? Well, that can't be right. It's polar covalent. All right, so I haven't done any math, haven't really looked at the periodic table at all. I just know that's a metal and a nonmetal, ionic. That's totally nonpolar. All right, so we're looking for things with polar bonds. Based on the periodic table and our rule that what's the most electronegative element? Fluorine. And what's number 2? Oxygen. Oxygen's number 2. And we'll dig on that a little bit when we talk about redox, right? It's what it's called oxidation, is because what oxygen's doing. If something's oxidized, oxygen pulling the electron away. Okay, that's what we got there. Okay, let's look at this one. So the difference between oxygen and fluorine on the periodic table, are they close or far away? They're pretty close. This is 3.5, and this is 4, so that's going to be 0.5. Okay. Nitrogen and oxygen, they're pretty close. Okay. I don't remember nitrogen. I think nitrogen's what? Nitrogen's 3. So this is 3, and this is 3.5. So the difference is 0.5. Carbon and oxygen. Oxygen is. Carbon is 2.5. So that's 1. It's A. Y'all okay with that? Okay. Yes?
How did you, like, I don't understand how you immediately know it's a polar covalent.
Because it's a diatomic, and they're 2 different ones. I know for a fact, so we talked about this the last time. The only true covalent bonds are the diatomics. Because otherwise, even between things like carbon and hydrogen, which are not very polar, they're still a little bit of polar. So you start with these things that are purely nonpolar covalent, and we just call those covalent once you get into AP. We don't really talk about being nonpolar, but I'm using that term because I want you to put it together. The only pure covalent bonds where everybody's equally sharing, because remember, covalent is sharing. The only time that it has equal sharing is when both atoms have the exact same electronegativity, and the only way that happens is if they're exactly the same, right? So 2 oxygens bound together will have a difference of 0. They are exactly the same. There's no reason for the electrons to favor one atom over the other atom. All right? So that's what makes that nonpolar. Everybody else has some amount of polar to it. Now, if it's not very much, we kind of ignore it. That's what this 0.3 is. We call that nonpolar even though there's a little bit of polarity. We want to make sure that we've got, I think there was a picture, but there's this scale that goes to ionic, okay? And we talked about the fact that polar compounds have a bit of an ionic nature to them because one side's more positive and one side's more negative. That actually helps bring them together, okay? They're slightly, because you have a polarity, you have a slight ionic nature. In other words, one's different than the other, okay? Did that answer your question? Okay.
So, question, would the reason for like fluorine having being the most electronegative, would that be because it's holding on to the electrons much tighter than the other atoms would?
It is. It has to do really with the what we call the shielding. So if I look at chlorine, so fluorine only has, I'm going to say, one hole, right? If I have the nucleus here with 9 protons, I have one layer that's filled, my 1s2. Then I have another layer here. Put a little hole there. Okay? So an electron that wants to get to the nucleus, this hole between the nucleus, the distance between this, right? It wants to fill this. It's got 9 protons reaching out, trying to pull in another electron from somewhere. I look at fluorine. What do we talk about with Coulomb's law and attractions?
It's a lot smaller.
It's a lot smaller. This distance is much closer than, let's say, chlorine. Chlorine has 17 protons, right? So chlorine with its 17, let's just put 17 protons here. Okay, it's got the 2. Okay, and then you got that distance, right? Bigger. What's going on here is, in order for this to get placed here, this electron has to deal with the repulsive forces of these electrons that are close to it. The electron that has to get here has to deal with the repulsive forces not only of this electron, these electron cloud, but this electron cloud too. So this one just is just fighting the 1s electron cloud. This is fighting the 1s and the 2s and 2p. All right. So there's between where it wants to get and where it can get, you've got more layers of electrons that are trying to keep it away. All right. So it has, relatively speaking, the same amount of attraction. This one's got plus. This is 17. This has got 9. So you might say, well, you would think with more positives, right, it would be more attractive. The difference is you've got this repulsion force. This has got much more repulsion going on. All right, let's go to the next one. Which of the following is the least polar bond and yet still polar covalent? Now, we just did the math, so Everybody make a guess? Is it going to be A? No. B? Because B is what? Ionic. C? D? No. E? All right. Well, why are we getting maybes? What's the question here? So does A make sense?
I mean, overall, it wouldn't make sense if it were.
What did the previous question say? Which one was the what? The most polar. So this one's the least polar, right? So could it be A? No. Could it be B? Because B is what? Ionic. Could it be C? Maybe. D? No. All right. So we're now left with C and E as possible choices. Now we should do some math, which we did just a minute ago before I erased it, right? The math of this one, what's the value? 0.5. What's the value of that one? So, what does the question ask? Which of the following? So my answer is C and E. So, yeah. Be fun when we have test questions. We got to bubble in 2 bubbles.
No, I brushed it.
Your hair?
Yeah.
Yeah, the puppy dog looks the same way after you brush it.
Special brush. Thank you.
All right, cool. Put these in order. Now that you know what you're doing,
Wait, where are the numbers?
do you need the numbers?
I don't know. Yeah.
You don't need the numbers.
I don't? Okay.
Come on, look at the trends. This particular one follows all the trends, so you're okay. What? Yeah, it's A, B, C, D, or E.
Oh, like which one's in
Which one's in the right order? Good? Everybody got something written down? Okay. All you got to do is write down A, B, C, D, or E, and you'll be okay. All right. So first of all, what do we notice? They all have chlorine. They all have chlorine, right? So what am I looking for then? I'm looking for what? I just need to look at the other elements, right?
Yeah.
So which one is going to have the most polarity? Arsenic. Okay?
Wait, what?
Decrease in polarity. So the difference between the chlorine and arsenic is going to be greater than anything else.
Wait, why is it not right?
What?
Because we're far away, right?
nitrogen's bigger.
Because fluorine's number 1, oxygen's number 2, chlorine's number 3. We know chlorine has a very high electronegativity.
Wait, how's it? It's probably a dumb question. How's nitrogen not high?
What we're looking for is the difference. So you're right, nitrogen has a very high electron affinity. But if I have something with a very high electron affinity and something else with a high electron affinity or electronegativity, and I put those together, the difference between those, that's what determines polarity. Okay? Like 2 fluorines together is not polar. Even though they both have, each one of them would have an electronegativity of 4 on the Pauling scale. So 4 minus 4 is 0. I'm looking for the difference. So which one's going to have the most difference? Well, the most difference is going to be the one with the lowest electronegativity, in which case that would be arsenic, right? All right, that gets rid of this choice, and that choice. Okay? Very nice. Red one works. Red one works. All right. What comes after arsenic? In terms of phosphorus, and then finally nitrogen.
I thought they had the same.
Because what we're looking at is arsenic, phosphorus, and nitrogen. And again, if you have your periodic table out.
Oh, okay.
Yeah.
On here, they have the same electronegativity, so wouldn't N
What does?
nitrogen and chlorine. So wouldn't they be or just covalent?
Oh, yeah, it would be the least difference. Chlorine's actually slightly more electronegative, but yeah, it would still be the least difference, right?
Yeah.
Yeah. Everybody good with that? All right. Let's go to the next one. And there we go. Which case is the bond polarity incorrect?
Yes, it's basically like positive charge, negative charge. Just a good way to think about it.
Yeah, so these are for covalent bonds. You know, in ionic bonds, there's no sharing, and so there's a full formal charge, a full formal +1 or +2 or whatever. So like in water, you know, if we do water, we've got oxygen, and we say it's okay, right? Which one of these are correct and which one of these are wrong?
Hydrogens are losing electrons. Because hydrogens are losing electrons. So whenever hydrogen loses an electron, the oxygen gains more charge, yeah.
Which one's right?
A.
All of them except for D.
Is A correct?
Sure. Oh wait, no. A is the right one. That is D. No, wait.
We're looking.
In terms of this question, D would be correct.
Okay. So, is A the right answer? No, because A is correct.
Yeah.
Yes. Okay.
Just say is it?
Just say it. All right. Is this written correctly?
Yeah.
Because potassium's a metal, oxygen's definitely going to be more electronegative, so that can't be right. What about this one? This one's kind of a weird one. Because who's more electronegative between magnesium and hydrogen? Hydrogen's far more, way more electronegative. Okay? Because it's hydrogen, right? So this is a situation where hydrogen actually takes an electron. You know, we typically talk about hydrogen as being an electron donor, right? It's going to be getting rid of an electron. This is a situation where hydrogen's actually going to take an electron. That's totally okay. What about D? Yes.
So whenever I feel like you just answered this question, but whenever you're looking at the periodic table and you're trying to decide if oxygen or chlorine is more electronegative, can you just like take the top one and say on
I
closer
saw a
to the
video
top?
where
Sure.
it says the
Okay.
top one.
Yeah. And again, that's for that reason that I showed with the circles.
Yeah.
Because the ones that are higher are going to be have
the longer the big radius.
right. They're going to have a smaller radius. So the distance between the electron that wants to come in and the nucleus is going to be shorter. So there's going to be a higher attraction. Okay. So chlorine or iodine, which one's more electronegative? Chlorine's more electronegative. So the one that's more electronegative is going to have a partial negative charge. So is this correct? No. So this is my answer. And you could ask the same question here if you wanted to. Silicon and sulfur. Which one of those is closer to fluorine? S, right? Now they have the same period, but sulfur's going to have a higher effective nuclear charge because sulfur has more protons. So it's going to try to pull in those electrons a little more. Okay? Y'all good with that? Yeah. All right, cool. Good review. Looks like somebody learned something today. All right, when two nonmetals form a covalent bond, they're going to share electrons in a way that completes the valence configurations of both of them. This is not new information. I know it's been a while. You may have slept a time or two since you heard this last year, but just saying, both nonmetals attain a noble gas electron configuration. That is, they complete their octet. That's the little junior high way of saying things, right? Here we go. Let's try that. Okay? When a nonmetal and a representative group metal, right? When representative group metals, what groups do those belong to?
1, 2.
1 and 2, that's it, yeah. Okay, the ion forms, so the valence electron configuration of the nonmetal looks like the next noble gas. Nonmetals gain electrons to move to noble gas, and the metals lose electrons to go back to the previous noble gas. Okay, and that's why we know that group 1 is always going to have a charge of +1, group 2 is always going to have a charge of +2, because they're losing those electrons from their s orbitals, and those s orbitals are farthest away from the nucleus. All right. The state of ionic compounds. So ionic compounds are special. I don't think we showed this to y'all last year. We kind of alternate showing it and not showing it. When we have this crystal lattice, when these repeating formula units of positive and negative charged ions align themselves, they do it in such a way to maximize the attraction between the opposite charges and minimize the repulsion between the like charges. All right? These crystals are put together in such a way. Good, well, I'm going to mention this. So, how many of y'all have taken a crystal and hit it with a hammer? Or at least seen someone do that, right? What happens to those crystals? They break, they shatter. Okay? So you take that diamond ring your boyfriend gave you and you hit it with a hammer and it shatters into a whole bunch of pieces. Yeah.
Wait, really? Wait, so diamonds are
Diamonds can be really brittle though. They're really strong, but you can break them, but they have three-dimensional attractions. Yeah. The diamond pickaxe, definitely. Or the diamond sword. Okay? All right. What happens here? So let's envision these things together. What happens here, though, if I hit right on this column and I push this column down just a little bit?
The other one's going to go down, and the other one's going to go down.
Right. So all these guys are going to go down. What happens when I put this negative charge here and a positive charge here? They do what? They repel. And now that they sit here and they repel, as soon as they repel, they break off. So this is something we use when we're shearing crystals. As you can impact the force, you shift it a little bit and it snaps off. We'll talk about that as we go. So we'll continue to talk about that. But I want you to think about this idea of maximizing attractive forces and minimizing repulsive forces. Right? I mean, this is what you do when you look for a partner, right? You want to maximize your attraction and minimize your repulsion. Just to give you a clue, there is always something about another person on the planet that will repulse you, right? The opposite is not necessarily true. Just be aware of that, okay? And don't be surprised. Ions. Let's talk about the gas phase of an ionic substance. If I have excited an ionic substance to the point that it's in a gas, there's going to be very little interactions. This makes sense, right? The whole point of gas particles is that they're very, very far apart. So if I take this salt, which takes a tremendous amount of energy, I get it into the molten stage. And I think it's like 600 degrees Celsius or something to get salt melted. I continue to add energy to the point that these individual ions are now flying off of the salt mixture into a gaseous phase. At that point, gas particles are going to have very little interactions with each other. And that's all I'm talking about here. That's really what we're saying. So, because they're very far apart, because I've given them enough energy to break that that attraction, those positive and negative attractions, there's very little interaction. This is the point of being in a gas phase, is that particles are far enough apart that they're simply not interacting with each other. All right. Let's go through this. This is something that you guys have been doing for a long time. I want you to understand that. All we're doing is we're going a little bit deeper. You know how to write the formula for calcium oxide. Put the little charges and you crisscross and you simplify, right? Yeah, I want you to think about what's going on here. All right. Our valence electron configuration for calcium is argon with 2 extra electrons, and for oxygen is helium plus 6 electrons. Okay? So the electronegativity of oxygen is 3.5, much, much greater than calcium. So the electrons will simply leave calcium and join oxygen. And we'll now have a calcium cation and an oxygen anion. And then they'll simply stick together. So here we go. Oxygen needs 2 electrons to fill up its 2s and 2p valence orbitals and look like neon. That's the next noble gas. By losing 2 electrons, calcium now looks like argon. Just goes backwards, right? They now each have a positive 2 and a minus 2 charge. They're going to stick together just through electrostatic attraction. The strength of that bond will follow Coulomb's law. Right? So you got a plus 2 and a minus 2. That's my top numbers. And based on how big they are, that will affect the overall strength. And because of this, we're going to do the crisscross. They're going to cancel each other out. And my formula is CaO.
Would a plus 3 and a minus 3 be considered a stronger bond?
Yes. Of the reasonably same sized particles. So, yeah, so you could have like phosphorus. So you could have like iron 3 phosphide. Okay. Good? Y'all remember all this, yes? But I want you to like your brain to be clicking a little few more gears on them. Okay. So here's our charges. Group 1A in the electron configurations. Hydrogen. Notice that is the minus. So when hydrogen gains an electron, it looks like helium. All right. I just wanted to point that out. These are all plus 1s. These are all plus 2s. And again, our plus 3. Good? All right. Let's see. Metals in group 1A lose 1, lose 2, lose 3. 7A gains 1, 6A gains 2. Again, you knew this. I think the beginning of your 10th grade year, maybe even back in your 8th grade year, we took a periodic table, we colored them, we wrote numbers on the top, right? Yeah. Okay. Yeah, those days are fun, right? So, noble gas configurations, tin and lead and bismuth and thallium. These are post-transitional metals. Post meaning after, right? Remember your periodic table, you got that little diagonal, the metalloids, and the guys up here are non-metals. And you got over here your representative metals, and the guys in the middle are called transitional metals. And this other little baby triangle over here is your post-transitional metals. Okay? Representative elements. Tin can form 10 plus 2 and plus 4. Lead forms plus 2 and plus 4. It's in the same group, yes? You should really have a periodic table in front of you looking at it. If you don't have one, go get another one. Bismuth forms plus 3 and plus 5. Okay? Thallium forms plus 1 and plus 3. So if I'm looking at tin, my Sn, go ahead and write the electron configuration for tin. Just noble gas configuration is fine. So krypton, Okay. After krypton, it's right. That's 10. Yeah. 4d10. I think that's right. See if that's right. All right. There we go. Is everybody okay with that? All right. So we have a situation where 10 can lose these electrons and become +2, or it can lose these and these electrons and become +4. Notice my d electrons are going to stay in place, and that's because they're taking up that space underneath the 4s and 4p. Okay? They're actually below these guys.
Oh, I get it. 'Cause it's 4.
These are your valence electrons.
Yeah.
This is the point here. So can you all figure out what, this one's going to be the same. Okay? It's just you're also going to have an F in there, but you're losing S and the P. What about bismuth and thallium? What electrons might they be losing? And you don't have to write them down. I just want you to look at your periodic table and see if you can figure out what they might be losing. Everybody got some? What'd you get?
6s2 and 7p3.
Yeah. Yeah. Cool. Everybody good? All right. Ion size. So we've talked about this a little bit on some of those test questions when we're talking about, again, coming back to Coulomb's law. The size of the ions are going to play a role in determining structure and stability. In other words, the strength of the bonds, how ions act in aqueous solutions, and biological effects. So the ionic radii are going to be determined from measuring distance between two ion centers. And we know these measurements aren't exact. And I tell you that so if later on you get into some big discussion or somebody comes back and says that they've figured out how to move it, it's all about being relative to each other, right? If you've got a big giant ion, two big ions, we talked about this, the free response, you remember the lithium and the chloride versus the sodium and the chloride, which one's going to be stronger? Well, I know relatively speaking, sodium and lithium, right? Sodium's bigger than lithium, therefore bonds between the same anion are going to be stronger between lithium because it's smaller. It's also +1, it's smaller. It can get closer to the, for instance, chlorine. So the lithium chloride is going to have a stronger bond than sodium chloride. This is what we're talking about here. We know about the sizes of an ion. We know that anions are larger. I've added more electrons. There's more electron-electron repulsion, so they're going to be farther apart. I know that cations are smaller because we've removed energy levels. Okay, so we've shrunk down.
Oh, you mean larger and smaller relative to
Their parent,
Alright.
the neutral atom. Yeah, yeah. So, you know this in a periodic table, ion sizes increase down a group. So if the whole table was just filled with ions, you would know that the sodium ion is larger than the lithium ion. Right? Let's see. Isoelectronic. Iso means what? So an isosceles triangle has triangles that have the what? Same sides, yeah. So iso, same. So electronic, you all play with electronic devices. But electronic, in this case, we're talking about the same electronic configuration. We're talking about the what? The electrons, yes. So these guys have the same electronic configuration. Aluminum 2 minus, fluorine minus 1, sodium plus 1, magnesium plus 2, and aluminum plus 3. Among isoelectronic series, the same number of electrons in the same locations, the size depends on the effective nuclear charge. In other words, what's a simple word for that? What determines the nuclear charge? What determines the charge of the nucleus? Protons. It gets smaller, we get more protons. Because I get more protons, I get a higher effective nuclear charge. Or a higher nuclear charge, I should say. Okay? And the Z in this case is your atomic number. So which one of these is going to be smallest?
Fluorine. Oh, they'd all be the same. They all.
Oh.
Wait. No, because wouldn't it still be fluorine? It has.
This is a trick question. It's just oxygen.
So we're talking about the size?
This one.
It's not aluminum or magnesium. Yeah, it would be.
Really? I guess.
It's oxygen and magnesium.
Wait, because it has a bigger charge
It gets smaller
as the charge.
as the charge increases. Who's going to have the highest charge out of this group?
Aluminum.
Aluminum has how many protons?
Oh my gosh, sorry. Plus 3 charge.
13. 13. Oxygen has how many?
8.
8. Who's going to be smallest?
Aluminum.
Aluminum is going to be smallest because those 13 protons are going to be pulling in those electrons. Okay? Everybody's got the same number of electrons. All right? But we've got 13 protons. Okay? They're going to be pulled in. All right. Good deal. Everybody okay? We all good now?
Aluminum is the smallest.
What's that?
I'm not good. So, aluminum is bigger because it has more protons. Smaller.
Smaller. Yes.
Wait, so that means more.
But then
The-
that means you have to fit more protons in there. So it's
Oxygen is fluorine big.
They all have the same number of electrons. Yes,
Electrons
this is-
take up a lot of space.
They're isoelectronic. They all have the same number of electrons in the same shells and everything. Okay? They all look like neon. Okay? So aluminum has 13 protons to hold on to those 10 electrons. So it's going to be pulled in tighter. Okay? And then magnesium not so much, sodium not so much. Oxygen and fluorine now are actually going to be larger than their parents because they've got additional electrons. And those electrons are going to interfere with the electrons that were already there, and so they're going to be pushed out even further.
So,
But aluminum's the smallest, oxygen's the largest.
so the bigger like negative charge. They're not also bigger than their parent.
Yes, because they're the electron-electron interference.
is largest because it has least protons.
What?
Oxygen
is the largest, yes, because the fewest number of protons. So those 8 protons can't hold 10 electrons very tightly. Okay. There you go. Y'all good? So here's some examples. What's going on here? Lithium, these are just some tables of ion sizes. Don't need to memorize these. It's all good. All right. You can chew on that. So the one that's neutral, electronically neutral. So, yeah. What's that? Yeah, we talked about this quite a bit whenever we were doing the going over that free response. Yeah, that's good. All right, you guys, your turn. Decreasing size. All right.
Y'all isoelectronic. Is that the word? Or do we-
It would be the word if but is that the true? I don't know. Look at them. Use your periodic table.
Trick question.
Mine's two.
Or do we just switch?
They're in increasing order.
So they are the same.
Yeah, decreasing order. So they're in order already.
Therefore, they're all in order. Trick
Yeah,
question.
that is just
Try.
decreasing
Wait.
order.
So BR.
Because the
No.
ones that lose,
35.
the ones that
No.
gain electrons grow.
So it's
Ones
30.
that lose them
Oh.
become smaller. They all end up with the same noble, like
36.
relative noble gas.
Minus two. So they don't have the same. Right?
I don't know. What'd you say?
Yeah, I was.
Trick question.
It's just a trick answer.
Or trick answer.
What's that? I should put this on the test.
No, don't.
Oh,
I
yes,
mean,
please
yeah,
do.
'cause I was
Please
second
do.
guessing
Please do.
myself, and I'll put it like this.
I probably forget by the time of the test, but put it there.
Wait, when do we have a test?
That's a good question. We should have.
Okay. Can we make it like 2 months down the road?
Yeah, we'll just have 3 test days in a row.
No, okay, I'm like. No.
Only if we can party.
We'll do. When's eligibility?
Oh, you're gonna do that too.
So we'll do it right on the day before eligibility. Test what?
That should be after school.
After school.
And these online.
No.
Better be gross.
But don't even.
That's the biggest. Oh.
Good.
Wow. So different.
Everybody okay with this? Yeah, and we cover this stuff in baby chemistry, so you should be pretty good. All right. Your turn now. Go.
Oh wow, I feel like I've seen this before. Noble gas. Wow, that sounds like a choice.
I know it either goes with this or goes with this. What? That's all I can tell you. Oh, I think it's this.
Wait,
Good
don't
test.
they? Oh, wait, yeah.
Everybody got a guess?
I think it's a gas.
Okay. Is it C,
No.
No.
D,
No.
B?
Absolutely not.
Okay. So because these are all in the middle, yes?
Yeah.
Yeah.
So is it this one?
No.
This one?
Yes.
Very good.
Okay. Okay, can the whole test just be like this? Yeah.
We should have done that thing,
Like,
like when if we say answer, you just pause for a few seconds and look at us, like, just look of shame.
Yeah.
Explain, please.
So let's look at this. First of all, you got them on the periodic table, right? They're all isoelectronic. They all look like argon. So they're the same number of electrons. So if I'm looking for the one that's largest, I need the one that has the fewest number of protons. Okay, don't hurt the pen. Okay, if I'm looking for the smallest, I'm looking for the one with the most protons, which in this case would be the calcium with the 20 protons. Sulfur has, what, 16 protons.
I thought there was like a trend, like atomic.
So there is, but we're talking about ions.
Oh,
That's why you got to look at these charges.
okay. So it's
Everybody looks like argon in terms of electrons. These guys all have the same number of electrons. They're isoelectronic.
so you would look at the number of protons.
The number of protons.
Whatever element or ion has the most protons has the bigger radius.
Opposite. More protons means those electrons are being drawn in tighter. Okay?
And less protons stays the same.
It can't hold on to them.
Trying to think of it when like they always talked about it in like 7th grade maybe. I don't know. I remember when they always said like atoms are like 99.9% empty space, and then you have electrons on the very far outside. When it takes in the electrons, it decreases the radius a lot more than it would be adding it, because when you add protons, it adds it to the center, because the center is so tightly packed, it doesn't really make much of a difference. But the electrons get pulled in a lot more.
Okay, that's a little explanation.
Good job. All right. Hopefully that got picked up here. All right. Let's now talk about lattice energy. Lattice energy is the change in energy that takes place when I'm got these ions, these gaseous ions, and they're now going to stick together. They go from their gas state all the way to a solid state. Okay? That's the amount of energy released when an ionic bond forms its ions. Because the energy is released, it has what kind of sign?
Positive. Negative.
Negative. It's got a negative sign.
Mr. Grumpy.
Energy is leaving the system. Y'all started to get confused in physics yet?
Oh yeah, he told us about that.
Yeah.
I don't like
Because
it.
y'all
Confuse me.
getting ready to do energy, and they do it the opposite for some reason.
Yeah. Are you serious?
Yeah.
He's like, it's easy.
They focus on the surroundings.
Yeah.
We focus on the system.
We just talk about the system.
Wait, we go to him. No.
It's what you're doing to the thing you're interested in physics. But here, I don't care about that. That's what I'm interested in. Energy goes to Pluto. I don't care if it leaves the system. That's what matters.
That's necessary. This is unnecessary. Period. It really is. Yeah.
All right.
Been confused.
So let's take a look at lithium fluoride. Okay. So we're going to take solid lithium. Solid lithium is going to go straight from a solid to a gas. Yeah, you take lithium. Okay. The enthalpy of sublimation is 161 kilojoules per mole. If I need to put 161 kilojoules, and I can take a mole of lithium from solid to a mole of lithium as a gas. Okay. The ionization of lithium. Now, this is where I have my lithium particle moving around, and I need to add so much energy to it that an electron will fly off. And so this is the first ionization of lithium, which is 520 kilojoules per mole. This is our ionization, right? Lithium, I need to put 520 kilojoules per mole to rip an electron off of it. Now I have a lithium ion. All right? So now I'm ready to do work with lithium now, because I've got this lithium plus 1, right? And I've got this extra electron floating around in the universe somewhere. Okay, well, we're going to come back to that electron in just a minute. I've got the dissociation of fluorine molecules. Remember, fluorine doesn't occur by itself, right? Fluorine is one of our what? Diatomics, right? It's one of our Brinkelhoff diatomics. I need to break apart the FF bond into single fluorine atoms. This is something fluorine doesn't want to do, right? It's happy in its low energy state here. So I'm going to have to add some energy into that. I'm going to take a half a mole, right? The energy here is 154 kilojoules per mole. But since we really only care about dealing with a half a mole, we're going to talk about being half of that, 77 kilojoules, to break the bond. I again have to put energy into the system to break that bond apart. So now I've spent energy getting lithium from solid to a gas. I've spent energy tearing an electron off of the lithium. I've spent energy breaking that FF bond. Good? All right. So the F, though, by itself doesn't like that state because it only has 7 valence electrons. And how many does it want? 8. A lower energy state would be for it to have 8 electrons. It finds this electron that happened to be floating around in the universe, and it sticks. And in doing so, it achieves a lower energy state, and therefore it releases energy. Okay? So this happens to be the electron affinity for fluorine. Remember I told you last time there's a little, while the trends tend to stay the same, there's a little bit of difference between electron affinity and electronegativity. Electronegativity is attractiveness for electrons in a bond. Electron affinity is talking about this. So now I have a fluoride ion in the gas form. All right, got that one. Now I have my lithium ion, my cation. I have my fluoride ion, and they're going to come together and form a solid. For this to happen, they both need to lose energy to attain this lower energy state. And the lattice energy for lithium fluoride is 1,047 kilojoules per mole. Because the energy has to be released, it's going to have a negative sign. Okay, so this is how we make lithium fluoride. You notice we had several little steps we had to get through. We had to move up, put energy in, energy out. All right. So here is the sum of the 5 processes for the various reactions. Okay. The energy changes, and this is our net. So going from solid lithium and gaseous fluorine, we get lithium fluoride solid and a release of 617 kilojoules. Y'all okay with that? All right. This is what we're talking about in terms of the energies of formation for lithium fluoride. These are the various steps. This is a table. So this is my net. I started out here, put energy in, a little more energy in, energy came out, and a lot more energy came out. This is our net change. If I started here, I lost energy. This is favored because overall it is a lower energy state. Okay? Remember, chemistry is all about finding the lowest energy state. All right, so here's our calculations. Does this formula look somewhat familiar? Gravity, or in chemistry we care more about Coulomb's law, right? So lattice energy is this lattice constant, charge, radius, right? This same formula shows up all the time. All right, this proportionality constant is depends on the size and structure, okay? And you figure that out. Again, I'm just pointing this information out for you so you can take a look at that. All right. Yeah, it's a modified Coulomb's law, right? Lattice energy has a negative sign when their charges are opposite. That means that they're attracted to each other. Yes.
What is the R? Oh,
It's a distance between the centers. Okay. Again, these are negative because it's an attractive force when they have different signs. It's going to be positive if it says repulsive force. If they have the same signs, it's going to be repulsive. They're going to have a positive. Okay. The process becomes more exothermic. In other words, energy has to be released for it to happen as the ionic charges increase or as the distances decrease. Makes sense? It's going to get bigger numbers, right? More attractivity, more attractiveness. Or it's going to take more energy to break them apart. However you want to think about it. Let's see. We got to balance the energies to form the charged ions. So you can imagine aluminum to become we got to get 3 electrons off of it, right? The first ionization energy is just the energy required to take the 1 off. But in order for aluminum to become the aluminum ion, we've got to take 3 electrons off. Okay, and then we're going to balance that with the energy released when the ions combine. When they pop back together, okay? Let's take a look at this. Which of the following ionic compounds is going to have the largest lattice energy? Look at your periodic table. Which one of these is going to have the largest lattice energy? Everybody got a guess? Everybody's written down A, B, C, D, E, or F. All right, let's look at A. So what's the charge of cesium? +1. Iodine is? Okay, so I got a +1 and -1. That's good. Are these relatively big or relatively small? Yeah, both of these are pretty big, right? So do you think they're going to have a very strong attraction between them? No. Okay. What about sodium and chlorine? So sodium's got a charge of +1 and chloride -1. That's kind of a guy in the middle, right? Chlorine's second row, and then sodium there. Pretty strong. All right. We'll keep coming back to that. I'm going to get rid of this because these guys are big. How about lithium and fluoride? Lithium's got a charge of, and fluoride. Okay. Size? Small, like smaller than sodium and chlorine, right? I'm going to go ahead and get rid of these guys, right? Let's go with cesium and fluoride. So cesium is +1. Fluoride is -1. What do we know, though, about cesium? It's big. So definitely compared to lithium fluoride, I would get rid of that one. Yes?
I thought if there were more protons, it was smaller.
So when we're looking at an isoelectronic series, so if I was comparing cesium +1 to iodine -1, cesium would be smaller.
Oh.
Okay.
Just like with the bonds.
Right, but that's the case when the electrons are the same. When I have the same number of electrons, then I have to look at, for size, I've got to look at number of protons. Magnesium has a charge of +2. Oxygen. So what do we think is going to have the strongest attraction? Yeah. Yeah, your +2, -2, those charges are gonna override any effect by distance. Good? Appreciate it. Like I said, this is stuff like we've talked about, but we've never really dug into the why. That's what we're doing here in this unit. All right. Let's talk about the partial ionic characteristics of covalent bonds. Now, ionic bonds form because of, what's the fancy Nancy word? Difference in charges. So what's the fancy? What kind of attraction?
Coulombic attraction. I don't know. Attraction. You said one.
Chemistry.
I already forgot the question now.
Chemistry, okay.
Chemistry.
I'm going to let y'all hang on that one. Okay. All right. Covalent bond between two identical fluorine atoms, right? So everybody's all balanced. If I'm looking at this, the electrons are spending more time here and here, right? It's overall balanced. I've got a little less electrons on the far outside because I got these two guys here. The electrons really want to stay close. And if I had a choice, I'd even hang out between these two, even the more favored spot, okay? So that's good. On the other hand, I look at hydrogen fluoride here, has both ionic and covalent components, right? I've got this idea that I've got this partially negative atom, and there's some attractiveness with the partially positive atom, okay? And I look way over here at some ionic bond, random bond, sodium chloride, doesn't matter. Could be sodium, this could be sodium and chlorine stuck together. There's no electron sharing. What we're saying is these guys are held, and here's your fancy Nancy word, electrostatic. They're held together by an electrostatic attraction, just a positive and negative stuck together. Okay? Positive and negative stuck together, electrostatic attraction. That's your ionic bonds. Nobody's sharing here. If I go looking for those electrons, they're right here. I'll look for them again, oh, they're right here. I'll look for them again, oh, no, they're right here. This guy's holding the electrons. This guy has given up his electrons. They're just sticking together through electrostatic attraction. All right. I can actually figure out what the electronic characteristic of a bond is. Are you going to be asked to do this? No. But I want you to see that you can actually do some math and calculate this. You may have a problem on it. I don't think there are. Okay? You can actually look at the dipole moment, the measured dipole moment, divided by the calculated dipole moment, or the theoretical, and you can see how much effect this drawing a little bit closer is going to have. That's all we're saying. And so you can see the ionic characteristics of covalent bonds and the electronegativity differences of these bonded atoms. Okay? So this is iodine bromide, right? Very little change here. HCl, covalent. But you notice we've got a pretty significant ionic contribution, right? There's a pretty significant ionic contribution to the bond. Let's look at this guy. Hydrofluoric acid, or hydrogen fluoride as it's written here. We're not thinking it's mixed in water, right? We're just saying it's all by itself in dry air. Hydrogen fluoride, okay? It's got a very significant contribution from the ionic properties, okay? Fluorine, it's got that 4. Hydrogen's 2.1. They've got a difference of 1.9. Basically, while we say they're sharing electrons, this electron is really spending its time around fluorine. Fluorine might as well just have the electron. And they're just sticking together. They are sharing the electron because it's a covalent bond. But it's because of that, that hydrogen, which is very positive because the electron's spending very little time there, and the fluorine, which is very negative because the electron's spending most of its time there, are going to have an attractive force together. And this is going to create this covalent bond that has a lot of ionic properties. This is what we're talking about here. So these guys down here, even HCl has got some. Notice these guys don't have terribly very much here.
Why is it so that as the atom, the anion, why is it so that when it gets smaller, it gets, well, it holds more ionic characteristics?
So if an anion is smaller, the electron's more likely to spend more time around. It's got higher electronegativity, right? Because of that, because it's got a higher electronegativity, the electron's spending more time, you're going to say it has a more negative property. And again, if you'll do the math, you can actually see this has got a difference of like 1.9. And so you can see, you know, we gave you that very rough estimate, but you can actually do math here. And you'll notice basically all these guys who are red, we're going to call those ionic, and these guys down here we typically call covalent. And you notice the differences here. These are all metals and nonmetals, right? And these are all nonmetals. Except for our good friend hydrogen, who likes to be its own. Okay? All right. Ionic character increases with these electronegativity differences, but none of these bonds are actually 100% ionic. So we never talk about having individual bonds as being completely ionic. Y'all good? All right. Again, seems overwhelming. This is stuff you've heard before, but I'm just going over it a little bit deeper. Many substances contain polyatomic ions. The bonds within these ions, if I'm looking at sulfate, that SO4 minus 2 ion, the sulfur and oxygen bonds in sulfate, those bonds are covalent. It's important to remember those bonds are covalent. Okay? Y'all good with that? All right. How do I figure this out? Well, we can go back to our definition of an ionic compound. And that's this. A compound that conducts an electric current when melted. If I can turn it into a liquid and run a current through it, that's ionic. That's our actual definition. This is where we came up with this. We've told you some shortcuts, you know, metals and nonmetals, and we've said this and that. This is how we actually tested. Is this compound ionic? The way you can tell is you melt it and see if it runs a current through it. All right. Let's talk about covalent chemical bonds. Bonds, really all they are is they force you to act as a unit, right? So any of your groups, a lot of us are part of other groups, and you work together as a unit. So you have a bond that you have to make in order to work together as a unit. This happens when the system is seeking its lowest possible energy. Does it make sense for this group to bond? It does if you want to achieve a low energy state. Okay? These occur when it requires less energy. If it requires more energy, you don't want to go there. You want to spend little time as possible, the lowest energy as possible. So they will form a bond when the resulting energy state is lower than their current energy state. And in order to form that bond, we've got to get rid of energy. Good. Let's see. We got some models that depict the molecular stability. Methane has this tetrahedral structure. This idea of bond, the way we draw them, is something we put in our brains. It's a model, and again, going back to that video we showed you last class, that's a model of what's going on. This is a method of dividing up energy to figure out when a stable molecule is formed from its components. Just a way to think about it. Models attempt to explain how nature operates based on experiences in the macroscopic world. And they originate from observations of the properties of nature. All we're doing is watching how nature behaves. This is a classic science thing. We watch how nature behaves. We build a model and test it. And we keep asking, is it behave like this? Yeah, okay. When it stops behaving like this, we break the model. We don't go back and say, well, nature must be wrong. We break the model and we start over. This is what's gotten us to this point. And we all know if we're good scientists, we're going to keep breaking models and keep moving on. All right, so the bonding model is a framework that helps us think about how chemistry behaves. They are perceived as collections of components. Makes sense from a physical perspective. Let's think now about bonds. This actually brings us to the table that we were talking about. Single bonds, we're sharing one pair of electrons. And double bonds, 2 pairs of electrons. Triple bonds, 3 pairs of electrons. There is no such thing as a quadruple bond. This should make sense, right? There's no way for me to align this model in such a way that I can have all 4 of them pointing towards you. I can get these 3, I can get these 3, I can get these 3. I can't get all 4 pointed towards you, so we're not going to have a quadruple bond. Those of you at home, this is the model we're talking about. I can't have all 4 of them pointed at you. Okay? The number of shared electrons causes the gap between the nuclei of the 2 atoms to close. So the more electrons that are shared, the shorter the gap. Again, stuff we went over, we're just talking about the why. Here's some bond energies, bond lengths and bond energies together. This is table 8.6, right? Okay. Energy must be added to the system to break the bonds. Energy is released when bonds are formed. I know your biology teacher may have lied to you. Energy is released when bonds are formed, not when bonds are broken. Energy is released when bonds are formed, not when they are broken. It requires energy to break bonds. And that should make sense because the bonds were there in the first place because they were at a lower energy. The bond formed because it was the lowest energy for it to be. I need to add energy to break those bonds.
Like with that reaction that we saw, like a few slides ago, adding energy can lead to a reaction which eventually gives back more energy than you put in.
Exactly. Now that's true. That's true. But the idea that breaking, you need to get the idea, breaking bonds requires energy, forming bonds releases energy. Okay? And this should look very familiar. I can look at the delta H. You all seen delta H before, yes? Delta H is the sum of all of the energy required from breaking all of those individual bonds minus the energy released from forming all of the bonds. And you can use those little bond charts that we just looked at, the 8.5 table, 8.6 table, and add bond energies together. Okay? Bond energy, you're always going to put a positive on bond energy, right? So the bonds being broken are here, the bonds being formed here, the minus here takes care of all that. Okay? And the N is just simply how many moles. So if you had 4 moles of carbon dioxide that you needed to break apart, you'd have a 4 here, right? Right there, the N. Good? We're going to start next class with that one. Cool. All right. So be sure to, if you haven't read the chapter already, get that taken care of. I'll go ahead and post some homework problems for you to do because I don't want you bored and you need to get working. They'll be due Friday. Well, yeah.